Dear learners, welcome to the course on Quantum Electronics 2 again. Myself, Arpon Deashi, Faculty of RCC IIT, welcome you to all on the second lecture of Quantum Electronics. Before going to the details, let me just remind you what we have discussed in our lecture 1. We have said that how a heterojunction can be formed, what is the difference with the homojunction, and in that respect, we have defined two fundamental energy parameters derived from the Mendel's periodic table, and those are work function and electron affinity. And we said that every measurement from now onwards will be made with respect to the vacuum level, that is energy equals to 0 line, and electron affinity is discussed as the energy required by the electron to move from conduction band to vacuum level, whereas work function is the energy required to liberate the same electron from Fermi to vacuum. And in that context, I reminded you that the photoelectric effect discussed by Einstein deals with the metal where both conduction and Fermi level are exactly same, so there is no difference between the work function and electron affinity. However, when we have to deal with the realistic semiconductor, we have to deal with these two terms, and all of our calculations will be based on these two fundamental parameters. In this respect, we further progressed and we said that heterostructure can be classified in three different types: type 1, type 2, and type 3. Type 1 is known as straddling, type 2 as staggered, and type 3 as broken gap. For both the cases, that means all the cases, we have given realistic semiconductor example. If you forget, go to my YouTube channel, you can subscribe, you can view this lecture. The presentation is also uploaded in SlideShare. And with that classification, we have taken a realistic example of gas system composition, where we have shown that why quantum well in conduction band is more important than that formed in the valence band for hole. And for mathematical preliminaries, we have considered Ben-Daniel-Duke boundary condition, which is first published in 1966. It's a famous peer-reviewed journal. And we show that the normalization with respect to effective mass is very important, as effective mass varies not only from material to material, but inside a material from point to point. But we have not discussed how a realistic quantum well is formed in our lecture 1. So once we have to introduce the term quantum well, let me go to our high school level topics, or topics which is made at our undergraduate beginning in the quantum electronics chapter or quantum physics course. That is a particle in a box problem. So we have to recapitulate with a particle in a box problem, which starts with the well-known Schrodinger equation. And I have shown the quantum well, that is an infinite depth quantum well at the right side, whose length is L. And the boundary conditions are between the quantum well, that means the inside between 0 to L, the potential is 0, and outside it is infinite. We have substituted this in the well-known Schrodinger equation. It becomes an equation of the SHM, simple harmonic motion, like the differential equation of second order, where there is no first term, first order actually. So we have solved it, and we get the expression of the eigenfunction, which is proportional to n squared. What does really mean? That the lower energy level is E1, if it is, then the next will be 4E1 and 9E1 and 16E1 onwards. So that should be our beginning from where we have started our journey of the world of quantum physics. But today we won't move according to this ideal structure or this calculation, but we have to dig into the problem. We have to make introspect a little bit more and find out whether this solution is really acceptable in our realistic world or not. We have to think a little bit more details. The way we have made the mathematical solution is really feasible or not. If we apply the same technique in our known nanoscale devices, whether it will give me a fruitful result or not. So there are several questions that will be associated in the particle in a box problem. Unfortunately, when we have started the journey of the quantum world, we have never thought of these things. So let me start with the queries that are very closely associated with the starting problem in the quantum mechanics. And from that we will find that if we have to really think about a real structure, then how the variations can be incorporated, how it will lead to my actual answer or very close to my actual answer, how much it is fruitful or not. So from that point onwards, with our existing prerequisite, that means the knowledge of heterostructure, the knowledge of Schrodinger's wave equation, and the other factors which we have taken into account, that can be merged with our concepts, and we will proceed further. So let's start with the beginning of the quantum electronics, and we start with some queries where we have to really think that how far this derivation based on which we are first become familiar with the terminology called quantum well, how far it is practically feasible. Let's think about the very known factor that what will be the material outside the well. We know the inside material may be silicon, maybe gallium arsenide, maybe indium phosphide, maybe whatever, a semiconductor. But at that time, generally textbook doesn't mention about the outside material of the quantum well. Please think on more details. Some textbook maybe mention it's a air. Let's say assume it's air. That means a quantum well, a manhole, is floating in the air, going anywhere in the world. Is it possible that in air a realistic semiconductor can float, can go from one point to another point? From our known observation around our environment, we can't say that it's never possible, but at the time when we have started the solution of the Schrodinger equation for this quantum structure, we have assumed, okay, I didn't bother about the material outside this quantum well. And what are the boundary conditions what I have mentioned? If you look at more details, the boundary condition says V equals to infinite. Now, is it really feasible that a potential barrier becomes infinite? Practically possible. How you can make an infinite long quantum well? If you even tunnel in the earth from North Pole to South Pole, even that potential is not infinite. It's height of physical height. How can you make the potential infinity? That means kinetic zero. are never possible. Everything you can't trap. So if that is the situation, if you can't trap everything in the world, then how could you say that I am giving a potential well which is infinite height? Sorry to say, it's never physically possible. Now, with these 2 points, once we getting these 2 points, then the question will be, if there is not air, there will be a material outside the semiconductor. There will be another semiconductor or something else. So there will be some electrons, no doubt, outside of the quantum well. And if these electrons come inside the quantum well, how we can assume that both the electrons or the same electron has constant effective mass? Extremely sorry, as far the derivation is concerned, we know that electron mass will vary from point to point. Forget about material to material. Obviously, it will vary from material to material. It's a materialistic property. So we can't take that effective mass becomes really a constant parameter. Even if it is air, from air to material, the effective mass will vary. But at that time of derivation, we are never bothered about the effective mass outside of the quantum well. That means in the barrier region. So again, the problem continues. We don't know what will be the electron effective mass. It's a real problem we have to face. And the last problem, the mathematical problem we have discussed in our lecture 1. That is, we have considered step potential. That's a rectangular potential well. But for any step function, please recall in your signal system class, for any step function at a particular value of x, you have two different values of y. Please think. Any step function will give it. At a particular value of x, you have two different values of y. It's practically impossible. And that's why in the previous class, we have considered so many different types of potential configurations: triangular, parabolic, Gaussian. I have mentioned also post-Taylor. These different potentials, why they came into market? Because rectangular is idealistic. Nobody in the world can fabricate a pure rectangular potential. From semiconductor technology fabrication point of view, this is never possible. So what we have to do? We have to incorporate all these queries in our solution. We have never thought of material outside the quantum well. We have to think. We have not thought that V can't be equals to infinite. We have to take a finite value of V. We have to consider different effective mass inside and outside of the well. We have to consider, if there is step potential, it can't give you my solution. We have to consider the realistic band structure. That means the point number 1 deals with the material science. Query number 3 deals with both physics and material science. Query number 2 and 4 deals with the mathematics as well as material science. So again, recall at the beginning of lecture 1, we have said that mathematics, physics, and material science together will give you the quantum world. So all these queries which are made for this quantum well, the particle in a box problem, has to be solved in more details. So let's go into much deeper. Think about how really a heterostructure is formed or how a quantum well is formed. So in the next 2 slides, I will discuss first how a heterostructure is formed, and after that how a quantum well is formed. Let's make. First is, consider an algas gas layer. Simple, take a algas substrate. On the top of it, grow a gallium arsenide layer. You can use MBE, CVD, MOCVD, whatever technique, but you have grown a uniform gallium arsenide thickness. Now for our design of band diagram, I will take some imagination, just help it. Suppose you have two books placed in this manner in the book rack. But normally what we see in the book rack, books are vertically aligned. So if we just rotate the structure, imaginative, we will find one gas layer and outside one Al gas layer. Now this is a straddling type of heterostructure, so Al gas have a higher band gap than gas. So what will be the corresponding band diagram? That will be shown in the right side. And I have shown some energy levels in the gas, why it will be more clear in the next two slides. But that is basically nothing but a heterostructure with the band diagram. And we are mostly familiar with this band diagram in our earlier class. So from the fabrication point of view, a bilayer structure of two different semiconductors, different means difference with respect to band gap, can form a heterostructure, and that's the basic definition of a heterojunction. In either side of the junction, the semiconductor should be different, or the material should be different more precisely. It may be metal semiconductor, metal insulator, semiconductor, semiconductor insulator, whatever. But that is basically a heterojunction formation. Now, based on the concept, I am going to form the quantum well. So, I am erasing this diagram and I am taking a tri-layer structure. What tri-layer is? Tri-layer is Al gas. On the top of gas, I have grown another Al gas layer of a uniform thickness. Let's take now all the layers are uniform. So we will get three books, A, B, and again a second copy of A. It may be A, B, C, but later we will go to the asymmetric. Now we are considering A, B, and A. Now consider again the book rack problem. So it should be vertically aligned. It should be again A, B, A as well as in a book rack format. So what you will do? You will consider the picture like Al gas, gas, and Al gas. Now, how many heterojunctions are formed? Please look. A closer look will reveal that there are two heterojunctions. In the left side, one is Al gas to gas. In the right side, one is gas to Al gas. We have two heterojunctions, Al gas to gas and gas to Al gas. Now for Al gas to gas, you will get a band diagram. For gas to Al gas, you will get another band diagram. Because there is a single gallium arsenide layer, so these two band diagrams will be joined. So please, if we join them, the diagram will be looked like this, where the first brown and green for conduction and valence respectively gives the first heterojunction, and the right side it will get the second heterojunction. Now please think. The top, there is a deeper well, and that can be considered as a quantum well. Very simple. You have placed on the top and you go inside, you are trapped, so it will be considered as a quantum well. You are trapped there. So in that way, you can physically realize a quantum well. And it can be made by a tri-layer structure with at least two heterojunctions. Now, if this is the quantum well, the outside is not air. Outside has some other materials, in this case, L gas. So you can't consider everywhere there are air. No, that's a wrong concept. So the question will be asked that how you can really trap an electron or trap an hole in this quantum wells. One quantum well is formed in conduction band, another quantum well is formed in valence band. How you can really trap the carriers inside the conduction and valence? That will be a question. So let's go. Now the carrier trapping phenomena inside the double heterojunction device, which is alternatively called a quantum well. So for that, our queries is how carriers are trapped. So I start with this. This is our known diagram. I think nobody has any problem with this. We have already established. And for sake of calculation, just consider at least there is one energy level in conduction band and one energy level in valence band. Though I have shown two energy levels in conduction band, but at least one should exist. These energies are called eigenenergies. Now consider one electron is placed on the conduction band of L gas. That's in the pink ball. Now you have given some external force on the pink ball. What will happen? If you push the ball will start to roll. And once it is rolling, it will find that there is a whale and naturally it will go inside the whale. It's very simple. Basic foundation of the classical mechanics. So, once it will go inside the whale, it will occupy the lowest available subband in the conduction band. That means the lowermost eigenenergy level. So that electron, if its energy is lower than the barrier height, suppose barrier height is V0 and the lowermost energy level is E1. So if its energy is less than V0 minus E1, then it will be really trapped. Again, please consider. In the same situation, I am considering one hole in the valence band and the same force is exerted on it. Now, if electrons will go from top to bottom, the holes will go from bottom to top. So, if you push the hole, naturally the hole will go to the highest subband available in the valence band. So, hole is also trapped. So, both the electron as well as hole, both are now trapped properly. And both are trapped in the gallium arsenide region, which is the lower bandgap semiconductor. Now, if both these things are trapped, please look out their energy difference. The energy difference between the trapped electron inside the conduction band and the trapped hole inside the valence band is different, completely different, or maybe say larger than the forbidden region of gallium arsenide. So that means their energy difference is much larger than the energy difference of the gallium arsenide. So if we say, I am highlighting this just by moving, that if this thing I am now showing it in a just encroaching and That means I'm trying to more elaborate, so giving a broader view. Now I am coupling it. Once it is coupled, please think, this is called exciton. That means the electron hole pair which is trapped inside this lower band gap semiconductor, the pair is called exciton, which means exciton energy is much greater than the forbidden energy of the lower band gap semiconductor. This is a very key point from our analysis perspective. It's much greater. So in this way, carriers are trapped inside a quantum well, and that will help to play with these carriers later on in order to make a meaningful device. Now, how electron motion, the carrier motion, occurs inside the quantum well? We know that quantum well means two dimensions are restricted and one dimension is two dimensions are unrestricted. Sorry to say again, one dimension is restricted. So I am trying to draw these two vertical lines, which basically restricts my say z-axis according to the equation. And this is the electron. Now, if it is energy E1, then it will oscillate, or its probability density will vary inside this. That doesn't mean its probability density is zero outside the quantum well, but it will be negligibly small. So electron will oscillate inside the quantum well. Because its wave nature, it will obviously oscillate, but it will be bounded in this direction. You can't make this electron free. So it's totally confined in a particular direction, but it's easy to move in other two directions. Now please try to make another direction restricted. That means we are going to a quantum where. And how the electrons will be totally confined. It looks like a waveguide. Two dimensions restricted, one dimension open. If you pick up a hair from your head, it looks like a waveguide or quantum wire to you. But surprisingly, our hair has a diameter 50,000 times more than the diameter of a quantum wire. So, quantum wire is very, very small. Its dimension will be of the order of the electron dimension. Now make the third dimension also restricted. I am considering Cartesian coordinate. So you will get a quantum dot. Which means, I am going back to before the mathematics, I have to go back to the case again. Which means that it is totally restricted. Consider your childhood days, you are playing Ludos, consider dice of a Ludo, and you are putting a smaller object inside the dice. So it's look like a quantum dot. I'm just giving a imaginative explanation of this thing. So now the carriers are confined in all the directions. Let's add mathematics to this structure using the Schrodinger's equation. Now look, I have slightly modified with our known expression which I have shown in the second slide of particle in a box problem. What is that? Please think. I have not written m star written. I have not written m star. I have written m star z. That means I have incorporated the variation, that means the dependence of effective mass on its position. And if effective mass can be included inside the differentiation, which will be the second equation. Once you have to start the quantum well solution, you have to start with the second equation, where the positional dependent of the effective mass will come into play. It will have a bigger role than the conventional Schrodinger equation. We have to start with the second equation. Now incorporate your particle in a box problem. Let's consider step potential for the time being. We will modify it a little bit later on. But if I incorporate V equals to 0 in this equation, what will happen? It will be the V term will be eliminated. And the equation will be looked like this format, which is written at the top. Now I am adding my actual boundary condition, which is v equals to v0. I can't write v equals to infinite. That's absurd. So if I write v equals to v0, I am getting the second equation. Please look at there. The second equation gives a term v0 size 8. So the first equation is for well. The second equation is for barrier. So we have get two fundamental equations of well and barrier from the Schrodinger's equation. Let's try to solve these two equations one by one. First, take the well equation. Now, this is a second order differential equation of SHM. So just simply write in the form of SHM, so we have incorporated term kappa 1. What is kappa 1? 2 mw star ze by h cross square. What is mw star? It is the effective mass of the carrier inside the well region. That means it's a material parameter. Now this kappa term becomes a function of material. E is the energy, H cross is constant, but material has a very important aspect of the solution of the well equation. Similarly, please go for the barrier equation. Again, if you solve it, you will get another kappa term which is called kappa 2. Now, again there is a term called mb star, and what is mb star? It's the effective mass of electron in the barrier layer. So again kappa 2 is a function of material parameter. But please at this moment, please stop and think, make a very closer look. There is a term called E minus V0. If E is greater than V0, then there will be no trapping. Electron will go unescaped. Escaped. It can't be trapped. But if E is less than V0, then only you can trap it. Now, if E is less than V0, mathematically this term becomes negative, E minus V0. That means kappa 2 becomes an imaginary quantity. Well, you will get one wave vector which is real, which is 2 mw star into E by h cross square, which is for well material. You will get one wave vector which is imaginary, 2 mb star into E minus v naught by h cross square. Now look, the realistic approach gives an imaginary wave vector. We have never thought it in the particle in a box problem. So what is kappa 1 and kappa 2? These are the two wave vectors, both have material parameter dependence. And for E less than V0, the kappa 2 is imaginary. Again, we have to think about these factors more carefully. Once we go to the mathematical calculation using the numerical approaches from lecture 3 onwards, which will be available after a few days in my YouTube channel, and the presentations will also be available in the SlideShare account. You can just type some keywords and you will get that. I will make two lectures. One will be based on the TMT, another will be based on the PMM, and if time permits, I will go for FDTD also, or at least finite difference. Forget about the time dependent part, but I will make finite difference approach. But Schrodinger's equation will give you this sort of material parameter dependence. Now, if you go around it, where the physics of semiconductor device comes into place. Normally, we have a dispersion relation from our earlier classes that E equals to h cross square kappa square by 2m star. Fine. But for the real material, the dispersion relations are not parabolic. For some materials, it has several non-parabolic coefficients. Alpha, beta, gamma, there are several first order, second order, third order non-parabolic coefficients. Now in nanoscale, if you want to really incorporate all those parameters, you have to introduce this nonlinear dispersion equation in your programming. And that will give you more accurate result compared to the earlier cases. So, physics of semiconductor device comes into play, material parameters comes into play, realistic boundary condition we have added, real electron effective mass are considered, which is vary from material to material. The step function, for time being, please consider it, later we will also remove it. So step by step we are removing the queries by adding the real boundary conditions. And the electrons trapped inside the quantum well are called two-dimensional electron gas. What is that? If you am drawing a triangular well for this time being, you may take rectangular, Gaussian, whatever, post-Taylor. But for triangular well, there is a first look out the term gas. What do you mean by gas? It's a wave nature, very simple. So if I couple the term electron gas, that means electrons have a wave nature, and where the electrons are in the conduction band, we have already shown in the trapping, that slide, using some sort of animation. So electrons in the conduction band are considered. Now what is two-dimensional? That means these electrons are allowed to move in the two dimension and one dimension is restricted. That means we are considering the electrons inside a quantum well. So 2D is nothing but electrons confined in the conduction band of quantum well, and by virtue of the nanoscale we have to consider its wave nature, not the particle nature. We will just close this lecture with another very key important aspect of multiple quantum well. What is that? It's just a cascade of the heterojunctions. Say 1 to n, several heterojunctions are cascaded. Gas, L-gas, gas, L-gas, gas, L-gas, and like those things. Now what will happen if I make this cascaded? There are two terms very closely associated with it. It's sometimes called MQW, sometimes called superlattice. What is a superlattice? Superlattice is an MQW, but a special type of MQW where the wave functions between the adjacent quantum wells can help carrier transfer through quantum mechanical tunneling. That means carriers can be transferred from one quantum well to another quantum well by means of tunneling process. How it is possible? I am giving some figures. Please look at them. The first figure is the superlattice, where the adjacent or the sandwich barrier between the two quantum wells is negligibly thinner. So the two wave functions, which are the solid lines, they have overlapped. Then their envelope function, which I have shown in the dotted line, fine. It shows that then tunneling can occur because the wave function overlapping. Whereas in a normal MQW, which is not a superlattice, is shown in the bottom side, where, look, wave functions don't overlap because the thickness of the sandwich barrier is much larger. So that means I will end up the slide with the say that the adjacent or the sandwich thickness will be very, very important once we are going for this purpose. So superlattice is a MQW where the middle barrier has much thinner dimension, whereas normal MQW, the middle barrier has a thicker dimension. Those are very key factors when we will discuss the concept of MQW and superlattice, and once we will go for the calculation of the energy levels, the middle barrier dimension will play a very vital role in determining this. So thank you all for today.